A substitution reaction is not going to happen nearly as readily as an addition reaction. And that's because we're starting with a reactant that is saturated. And when the reactant is saturated, that means it doesn't have any of those double bond electrons that can react quite readily. It has only single bond electrons. And so as a result, what we're going to need to help the reaction to begin, to help the reaction to happen, is something like light. Light can work well to serve this purpose because it can energize electrons, which can help to break bonds, or catalysts are sometimes used for this purpose as well. So the first example we're going to look at in this substitution is the reaction between propane and bromine, and we're going to have two products that are going to come out of this reaction. So one of them is going to be this 1-bromo-propane, and this is one of the possible places that bromine can end up. Unlike an addition reaction, we're going to have a second product. So we are also going to form this hydrogen bromide as my second product. And so we'll see why in a substitution reaction, we start with two reactants, and we're going to end up with two products as well, differently than an addition reaction. So let's start with the reactant. We have propane and we have bromine that are both floating around, and they can interact with each other. And what's different here is there is really nowhere that the bromine is going to like to attack the propane. There's nowhere that it can easily or readily attack. So that's why we need some light in order to energize the electrons and make the bonds more likely to break. So in the presence of light, as the bromine comes in, it can attack this molecule from underneath. And when it does that, it can cause the hydrogen-carbon bond here to break, and a new bond can form between the bromine and the carbon. So this is why we call it a substitution, because on the carbon, the hydrogen has been substituted for a bromine. Well, what about this other bromine atom and the hydrogen that just got kicked off? Well, they're not happy. They have unpaired electrons, so they're going to want to join up with each other like this, and that's going to be our second product, which can now float away and go and do its thing. And so this is one possible way that the reaction can happen. However, there's a second possibility, because if instead of attacking on this first carbon, if we had attacked on the second one, so here's the propane again, and if instead of attacking where it did, the bromine had come in and had attacked this carbon instead, then when it attacks this carbon and kicks off the hydrogen, the bromine would have bonded to this carbon over here. My second product, would still be hydrogen bromide, hydrogen with a bromine attached to it here. But in this case, in this scenario, I would have ended up with 2-bromopropane instead of the 1-bromopropane that I had in the first example. And you might say, oh, well, that's interesting, Mahaffey, but couldn't it also attack on this carbon on the end and bond there too? And the answer is absolutely, it sure could. And that could have happened instead as a third option. But if that had happened as a third option, it would not have been a unique molecule, because we would have formed not 3-bromopropane, but we would have formed just a different way to get 1-bromopropane, right? These molecules are the same. So there are two possibilities here from our product's point of view. We can either end up with the 1-bromopropane we saw in the first example here, or we can have 2-bromopropane, which could form in this example as well. So these would be our two possible products that we could get in this reaction. And that will happen sometimes with reactions. There may be more than one product that can form. And you'll ask, well, how will I know which one will form? And the answer is both will form. Sometimes one will be more favored than the other and will form at a higher ratio, right? We may have more of 1-bromo or more of 2-bromo, but deciding which thing is more favored is beyond the scope of our course. The one thing that you would want to note about our starting materials here too, compared to our products, is our reactants were both saturated, right? We had a saturated hydrocarbon that we were starting with, and then our products are saturated as well. So in an addition reaction, we started with something that was unsaturated, and we ended up with something that was saturated, or at least more saturated than the reactant. In a substitution reaction, the degree of saturation doesn't change. If we start out with something that's saturated, we end up with something that is also saturated. So here's what it looks like on paper. We have our substitution reaction. We have an alkane, saturated hydrocarbon, and one of the hydrogens is going to be replaced by one of these bromines that we have here. So in the reaction, we're going to have the bromine is going to come in, it's going to kick off one of the hydrogens and swap places with it. So my product is going to look like this, where my bromine is substituted at the second carbon. That's the result of the substitution happening right here instead. So these are possibilities, right? There are two possibilities that will happen. And so people will sometimes ask, okay, well, there are two possibilities. Well, which is the one that's going to happen? And like we said before, the answer is both. Both will happen in some ratio. So my two products then would be 1 bromopropane and 2 bromopropane. Now in this reaction, we have benzene reacting with chlorine. Now you might say, well, that benzene shouldn't do substitution because it's unsaturated, right? It's got double bonds. And you're right that it's got double bonds, but remember that benzene is not unsaturated. It doesn't fit into either the definition of saturated or unsaturated. But the thing that we did say about it when we started learning about it was that benzene behaves as if it's saturated when it reacts. And so when the benzene is going to react with some chlorine, it's going to react in a similar way as the chlorine would react with an alkane. So the chlorine is not going to do addition to the benzene. These delocalized electrons exhibiting resonance are too stable to do that. So instead, we can do substitution. The whole top of the molecule is where we can attack. The chlorine would come in, it would bump off this hydrogen here, and as we bump off the hydrogen, we would replace it with the chlorine. Then the hydrogen and the chlorine can bond, and they would form my product, my second product. So the reactants were benzene and chlorine. The products are going to be chlorobenzene and hydrogen chloride. So we have two products here as well. So here's our setup on paper. We have the benzene, right? It's aromatic, so it only has one hydrogen on each carbon, and these are alternating double bonds, resonant double bonds here. My diatomic chlorine here, and this reaction will happen in the presence of light and an iron chloride catalyst. So what will happen here, as we said, is the chlorine will come in, it will bump off one of these hydrogens, which is going to leave along with one of the chlorines. So my benzene ring will still be here as the backbone of my molecule, except that one of the hydrogens has been replaced with the chlorine. So that's it sitting here, and then I have my other product here will be hydrogen chloride.